So what we have to know in order to use RSA? So we have to work with primarity tests to generate keys, step 1. So there are 2 popular tests. First one is Fermat's primarity test. And the other one is Miller-Rabin test. Then the other thing that we have to do in order to use RSA as digital signature, we have to learn how to do fast exponentiation, because it is kind of slow if you try to do that with regular, just multiply, okay? So you can do that with square and multiply algorithm. And there is no other way to use RSA without it. Now, also to make it fast, you can use Chinese reminder theorem. Now, those computations can be only done on the side of the person who has the private key. You cannot speed up computations if you have only public key. Okay, so this is just for the person who signs this key. So we have so it can be used only when signing document. And we cannot use it to verify signature. And then the last thing that we have to connect here is how to compute private key. So the RSA digital signatures, they are beautiful in the idea that this is just exponentiation module something. So this looks like beautiful math, but in fact, we have to think about fast exponentiation. We have to think to use Chinese reminder theorem. We have to know some kind of modular operations and math with in rings in order to be able to compute private key. And we need to use primarity tests. So you can see more about it in my other videos. So there is some kind of an issue, in fact, 3 main issues with RSA digital signatures. So let me list those most important issues. So the issues are, the first thing is that if you think about it, so your signature is basically the encrypted message, okay? So you have a message and you attach to this message the signature that is basically of the size of the message. So what you send from one person to another, actually it doubles its size. So such naive RSA digital signature is huge. Okay, so there is an issue of like how much we have to send. Then another issue with it is homomorphic property of RSA. So without knowing private key, we can actually, if we observe communication between two people, and if you see two messages sent with signatures, then you are able to generate a valid signature for some kind of message that doesn't make sense. Okay, but you can do that. The third thing is that we call existential forgery. So it means that, again, you can kind of like generate fake, valid signature for some kind of weird message, okay, without knowing private key. So again, let's have a look at those three issues. So issue number one, big size of the signature. So signature is big. The second issue is homomorphic property of RSA. So what it means, so let's say that we have Alice, and Alice, she signs two messages, M1 and M2, so she generates signature S1 for first message with her private key D, modulo N, then she generates signature S2 for another message. Yeah, and let's say that she sent it to Bob. Maybe in the morning she sent the first message together with the first signature using the same private key. And then she sent another message with another with a different signature because it's for a different message, but it's computed with the same private key. So Bob receives those two messages, okay, he is able to verify those are from Alice. Now let's say that we have bet if. So what it can do, she can compute signature S3 as S1, S2, modulo N, and then surprise, this is actually a valid signature. This is valid signature for message M3 computed as M1 times M2 modulo N. Okay, so she can send this message M3 together with this signature to Bob. And now when Bob will try to verify if this is Alice's signature, the authentication will be positive. But notice that if she has no control over how this message will look like, okay? So she can generate a fake valid signature for some kind of a fake message, but she has no control over how this message M3 will look like, okay? So that's the kind of issue with naive RSA digital signature. Now the third issue with naive RSA digital signature is existential forgery. So again, we can generate a valid signature for some kind of message that doesn't have any sense. Okay, so how we can do that? So let's say that we have Bob. Okay, and then we have Bob has like private public key everybody can see that. And it's a pair of E and N. And then if, this is our Bob, when we have Eve that she wants to send some kind of message to Alice, so she will think it's from Bob. Okay, so what she can do? She can pick signature. Okay, sounds kind of weird, but yeah, she has to pick some kind of signature. And then she will compute corresponding message. So again, no control over what kind of message she can send, but she can make a valid signature for some kind of weird message. And it can affect communication between Alice and Bob. Computes corresponding. So she will compute it as M/S, this S that she wanted to use, to power E, public part of Bob's signature modulo N. Okay, then she can send this message that she computed together with the signature that she decided to use to Alice. And then Alice will compute. So she will compute M prime as S to power E modulo N. Right? This is how we verify signatures. And then she will compare. She will compare M with M prime, and what she will realize that actually, yeah, this is valid signature. Well, this is valid Bob's signature. Okay, so and then she will think like, what is this strange message from Bob? Okay, so. And she can wonder why Bob sent this weird message to me. Okay, but still she will think it comes from Bob. Okay, so look kind of weird, but yes, this is how we can fake signatures. So we can have, let's say, 3 and 77 here. Let's say that she would like to use S equal 10 signature, and then M can be computed as. Okay, so that will be 10 to power 3 modulo 77. So that gives us 76. So this is our M. So she sends 76 and signature 10. What Alice does, she computes M prime. And how she computes it? She computes it with as 10 to power E modulo 77. So of course it will be 76. Okay. So we have 3 main issues with RSA digital signature, but the good news is actually there is one solution to all of those problems. This one solution to all of those problems is use cryptographic hash function. Now, cryptographic hash functions, we cannot just use some kind of a hash function that used for hashing. It has to be cryptographic hash function. Okay, so actually in real world, we don't use RSA, this naive RSA digital signature. We always use it with cryptographic hash function. You can use, for example, SHA-3, which is considered very secure hash function. There's a better one and what we do when we have a message M, we compute hash of this message. Now remember, you have to use cryptographic hash function in order to do that. What hash functions they do? The idea is that you take as input arbitrary size message, and the output is fixed length size, some kind of hash sequence of bits. Usually it is 256 bits, but if you want to have a post-quantum security, then you should use 512 bits output of a hash function. SHA-3 can generate 512 bits of output. So we don't actually sign entire message, we only sign hash of the message. Now you might think, is it secure? Well, it is secure if you use the right hash function. Okay, so we generate signature by computing. We have hash of message m to power d modulo n. So this is our signature. So if we want to send the message, we send the message together with attached signature that is computed on the hash of the message. And then in order to verify the signature, we compute two things. So first thing is we compute hash of this message that we received. And we compute H prime. So we take the signature, it's just the number, signature is just the number here. So the signature that we received, and to power E, public exponent modulo n. Now if H is equal H prime, then it means that this is a valid signature for message M. So this is everything in this video. Thank you for watching, and you can learn more in my other videos if you are interested to learn also more details related to this digital signature. Thank you.